Graphing. Graphing is an essential skill for science, just like it is for math. And we've already talked about when we looked at the scientific method, the importance of it in forming relationships between variables. So variables, when I say variables, we have to remember that there's two specific types, the independent variable and the dependent variable. The independent variable is the variable that the scientist controls or sets in order to see how the other one will respond. It's independent of the scientist or the other variable because the scientist is regulating it. When we look at it, it always changes at regular intervals. Generally, if time is being measured, it will be time. So 0 seconds, 30 seconds, 60 seconds, etc. The dependent variable responds to changes in the independent variable. So depending on what the scientist has set for the other variable, it will have different values. Looking at the data set, quite often it will have irregular changes or values to it. Decimal numbers, or it just won't follow the regular pattern like the regular one or like the independent variable will. Now, when it comes to graphing the line, we have to consider that unlike in math where you get nice, perfect situations, science is hardly ever perfect. And so when we form graphs, we have to do a best fit. And a best fit line is used when plotting data because it will look at the measurements and we remember that they have some uncertainty. We can draw those with uncertainty ranges even. That's the importance of sig figs. We also will see that all points on the graph don't necessarily fall on a specific line that we can draw. That's why we call it the best fit line. The line is the best fit to the data that you were given. Now, to show uncertainty around specific points or data points, we can use uncertainty ranges. They're drawn as error bars if there's only uncertainty in one of the variables. For example, in the case on the left, we have specific years, 1980, 1981, 1990, etc. You're in a specific year, there's no error to that. But the responding variable, the dependent variable, does have some error. The measurement may be give or take a little bit. In contrast to that, if both our independent and our dependent variables have some amount of change, we're measuring time, which could be plus or minus a little bit depending on how precisely you can measure the time, and the dependent variable will have associated change just depending on the error that we're able to measure in it. And that will give you error regions. So we have to have a set of rules for drawing best fit lines. And there's three basic points to it. We can say that best fit lines are drawn so that, one, there's as many points above the line as there are below the line. That way we know that we aren't skewing the data in one direction or another. The errors average out. The line should also pass through as many uncertainty regions as possible. If we don't have uncertainty regions, then we're going to draw it through as many points as possible. And three, we want to have as many points on the line as possible, and we need to be careful for whether or not to include 0, 0. So when we're determining whether or not to include the point 0, 0, we need to consider whether a value of 0 on the independent variable necessarily causes a 0 value for the dependent variable. If there's no mass, then it occupies no space, for example. So that would include a 0, 0. But in contrast to that, if we have a temperature of 0 degrees Celsius, that doesn't necessarily mean that the volume of something would be 0. So that would be incorrect. What we say is that if you can draw a straight line through a set of points such that the line passes through all the regions of uncertainty, then you're justified in doing so. And that's actually what Excel does when it draws a best fit line. Now, once you have a best fit line, all other calculations are done from the points on the line because that line is assumed to have averaged out our errors. So that means that once we have the line, we have to measure slope and the y-intercept and determine the line's equation from the line itself and points that we can extrapolate or interpolate from the line, not from the data points. So do not use the points or values in your data table once you have that best fit line. Additional data can be taken from a graph by two processes, interpolation and extrapolation. Interpolation is using the line to find values either on the x or y axis within your data set. Inter means within, so interpolating means finding a value within the range of point values that you have. Extrapolation is the opposite of that. So that extends the line past the last set of points. It does assume that the trend of the line continues, and you can also use the equation of the line to predict the values, but it does fall on that basic assumption that the trend that you've created within your data point or your data range is going to extend almost indefinitely, and that may or may not be correct. So another method of finding information from a graph is by making predictions by finding an equation from the line. And there's three main types of relationships or graphs that are used in chemistry. I'll give you an example of each one, and then we'll talk about them more as the year progresses. Direct variation goes through the point of 0, 0, and it produces a straight line with a constant slope. This has the general equation of y equals mx. So doubling an x value will consequently double the y value. I want you to be really careful though, because final equations on a scientific graph should never include x's and y's. You don't actually go out and measure an x. That doesn't mean anything. You don't go out and measure a y. So you actually are going to measure things like mass and volume like we have in this particular example. And so we should use more appropriate variable letters like m and v to represent those in our final equation. You're certainly fine to start with that general equation of y equals mx, but you need to know that in your final answer you should get rid of the y and get rid of the x. Building on that, so when we look at the direct variation, you had a 0, 0 point. The only difference between a direct variation and a linear variation is that the linear relationship doesn't go through the origin, through 0, 0. So it has a y-intercept that we call b. It again produces a straight line, and it now has the general equation of y equals mx plus b. The nice thing is that you could actually use this linear variations equation to make a line equation for a direct variation. All we would have to do is set the b value to 0. Remember again that even though we have this equation that has y's and x's, we don't measure those y's and x's in science. So in our final equation, we need to substitute appropriately a more useful variable. In this case, we're measuring pressure and temperature, so maybe a P and a T. When we're looking at that general equation, remember that when we look at it, it has this term m. And m, just like in math, as you've learned a number of times along the way, m represents the slope. We can talk about that in terms of the rise over run, or a change in your x value on the bottom and a change in your y value on the top. Anytime you see this triangle, that's a delta symbol, and that represents a change. It's always a final minus an initial. Our final relationship or variation that we're going to look at is an inverse variation, and this happens in the case that you have one variable increasing and the other variable decreasing. The general equation for it is y equals kx, or in other words, we can look at this as having the two variables we're measuring on the same side of the equal sign. You would not be asked to produce the equation for this particular variation, but you would have to understand what it represents. Once you have derived an equation from the graph, then you can use it for making predictions by substituting values into the equation. You must assume, however, that that graph continues in the same manner as the graph had throughout the data range that you want to use. That is, the slope remains constant. So for example, if we're looking at the relationship that F, the degrees in Fahrenheit, is 1.8 times the degrees in Celsius plus 32, if we want to know the value of C, of the degrees in Celsius when you have a temperature of 212. We substitute 212 in, and now it's just algebra. Remember that when we do algebra, we're going to use the opposite of bed mass. So in other words, we're going to go by SAM/DEB. So the first thing we have to get rid of is this 32. So I'm going to subtract 32 from both sides, giving me 180. So 180 equals 1.8 times C. Now the only thing attached to that variable that I'm trying to solve for is the 1.8. When two numbers are written side by side, it means to multiply. So to get rid of the 1.8, I need to divide both sides by 1.8, meaning that the temperature in Celsius that corresponds with a Fahrenheit temperature of 212 is 100 degrees. If you were given the opposite situation and asked to find the value for F, when C equals -40, all I have to do is substitute -40 in. Now we have all numbers on the same side, so we just have to follow normal bed mass. We're going to multiply before we add or subtract, and we get a Fahrenheit value of -40, the 1 point on the Fahrenheit and Celsius scale that happened to correspond. So that's our introduction to graphing. In class next day, we're going to be working extensively with developing these skills. This is the last review topic in our introduction to chemistry. So be aware that within the next couple days, we're going to have our first unit test.